All right, let's just dive right into it. In this explainer, we're taking Chapter 11 of your science curriculum and turning it into, well, a sweeping cosmic journey. Whether you're just trying to cram for an exam or you genuinely love looking up at the night sky, we're going to break down the incredible science of stars and galaxies. It's a universe full of violent explosions, crushing gravity, and a scale that's honestly unimaginable. And it's all laid out perfectly for us to explore today. So we've got a lot of ground to cover. We're going to start with our place in space, then look at galaxies and their three cosmic shapes, dive into the birth of a star, follow that up with life cycles and star death, and finally we'll wrap up by classifying the night sky. Okay, let's kick things off with Section 1, our place in space. To truly grasp the universe, we first kind of need to anchor ourselves, right? Space is so incredibly huge that our human brains genuinely struggle to comprehend the distances. So building a mental map helps us figure out our cosmic address. We start right here on our home planet, Earth, which orbits the sun in our solar system. But you know, our solar system is really just a tiny little speck inside a massive swirling structure called the Milky Way galaxy. From there, the Milky Way belongs to a local group of galaxies, which is part of an even larger cluster of galaxies, and all of those finally make up the entirety of the known universe. That progression really puts our day-to-day lives into perspective, doesn't it? Moving right along to Section 2, galaxies and their three cosmic shapes. Now that we've established that mind-boggling scale, let's zoom in on the massive cities of space where everything actually lives. Galaxies are essentially these massive gravitational hubs. We're talking collections of millions, often billions of stars, along with huge amounts of gas and dust. And scientists basically classify them into three distinct shapes. First up, you have spiral galaxies, which look like these beautiful, glowing, spinning tops. Think Andromeda or our own Milky Way. Next are elliptical galaxies, which look more like flattened ovals or glowing plates, like Ursa Major or Messier 87. And finally, irregular galaxies. These don't really have a defined shape at all, usually because the gravitational pull of other nearby galaxies has totally warped them over time, kind of like the Magellanic Clouds. Our own Milky Way is actually a perfect example of a spiral galaxy. You've got this really dense, bright, glowing center, and then those sprawling, curved, spiral arms sweeping outward. But what's really wild is that our solar system doesn't sit in the busy, bright center of all that action. We're actually located pretty quietly, way out on the edge of one of those spiral arms. Basically, we live in the cosmic suburbs. And what's truly staggering here is the sheer volume of material out there. Our Milky Way galaxy alone holds approximately 200 billion stars. Let that sink in. 200 billion. And our sun, you know, the giant blazing fireball that provides literally all the heat and light for our entire planet, it's just one single, completely average, medium-sized star among them. Crazy, right? All right, Section 3, the birth of a star. So, how do these individual stars actually come into existence? Well, the universe is like this constant churning factory, and the nebular hypothesis maps out these incredibly violent, fiery origins. It all starts with a nebula, which is just a massive, freezing cold, floating cloud of dust and gases, mostly hydrogen and helium. Over hundreds of thousands of years, this relentless gravity begins pulling the cloud together. The material spins, it compresses into this super dense globe, and after about 500,000 years, the pressure in that core becomes so immense that the temperature skyrockets to millions of degrees. When it gets hot and dense enough, boom, it literally bursts into a shining protostar, born to shine for billions of years. The absolute most crucial point here is this intense nuclear reaction happening right in the core. Because the heat and pressure are just so extreme, hydrogen atoms are literally smashed together to fuse into a brand new element, helium. This process is called nuclear fusion, and it is the exact engine that powers a star. This one reaction is what releases all that brilliant, staggering light and heat energy that eventually travels across the vacuum of space just to warm our faces here on Earth. Which brings us to Section 4, life cycles and star death. But just like living things, stars don't last forever. Eventually, that nuclear engine runs out of fuel. And a star's ultimate fate? Well, that depends entirely on its mass at birth. The cosmic drama of star death starts out the same for all of them. When the hydrogen fuel runs out, the outer layers expand, and it becomes this massive red giant, or even a supergiant. But from that expanded phase, the star's destiny takes completely different paths depending on whether it started as an average, large, or super large star. Let's break down that split. An average, medium-sized star, just like our sun, will eventually expand into a red giant. but its core just doesn't have the mass for a super violent ending. So it's basically going to quietly shed its outer layers and contract into a really small, dense, cool object called a white dwarf. But massive stars? Oh, they go out with a spectacular bang. They contract so rapidly that they trigger a massive explosion called a supernova. We're talking an explosion so incredibly bright, it can sometimes literally be seen from Earth in broad daylight. After the dust clears from that, what's left is either an incredibly dense neutron star or, well, something far stranger. If the original star was super large, like the true giants of the universe, that supernova explosion crushes the remaining core inward with such unimaginable force that it literally rips a hole right in the fabric of space. It creates a black hole. The gravitational pull here is so incredibly strong that it just sucks all matter into it. Not even light, which is the fastest thing in the universe, can escape its grasp. And that is exactly why it appears perfectly dark, just this mysterious, terrifying void in the glittering cosmos. Finally, let's move to Section 5, classifying the night sky. After that wild cosmic journey of violent births and explosive deaths, let's bring it back down to our own backyards. When you look up at night, you aren't just seeing a flat ceiling of uniform white dots. You are actually looking at stars with vastly different characteristics. Scientists classify them by their size, ranging from tiny dwarf stars all the way to massive giants and supergiants. They classify them by their distance from Earth and by their apparent brightness. I mean, stars like Sirius and Rigel are some of the absolute brightest things in our sky. But honestly, perhaps the most fascinating way to classify a star is by looking at the link between its color and its surface temperature. Now, this is a highly counterintuitive cosmic secret. Down here on Earth, we naturally associate red with hot and blue with cold, right? Like the taps on a bathroom sink. But in space, it is the exact opposite. The red stars you see are actually the coolest stars out there, burning below 3,500 Kelvin. As a star gets hotter, its color shifts to orange, then yellow, which is where our sun sits, and then to white. And those stars burning at the absolute highest, most furious temperatures, those are the brilliant blue stars just blasting away at over 25,000 Kelvin. No way you'd guess that just by looking, right? Knowing that every single point of light you see is actually a massive nuclear engine living out its own dramatic life cycle, I mean, from a swirling nebula all the way to a potential black hole, it really changes the view, doesn't it? I really hope this explainer leaves you looking up at our universe tonight with a profound new sense of wonder. Thanks for joining me on this incredible cosmic journey. Keep asking questions and always keep looking up.